Okay, couple of things to talk about before going back to material. The first midterm exam is next Monday in class, 50 minutes, although I'll let people stick around until the hour, give or take. For the most part, after about 50 minutes, people are not improving their scores. So one thing to try to learn is when to stop working on the questions. These are questions that I write or have written, and as opposed to the homework questions, which are complicated pedigree, or no, what's the word for our, anyway, there's a word for where they come from. Anyhow, they're imperfect in various ways. For example, they have often a best answer and the less good answer. My questions are, I think, always, they have a right answer and 3 wrong answers. So you can take the exam in principle 2 ways. You can look for the first right answer and then you're done. Or you can identify the first 3 wrong answers and you're done. So in effect, if you can really look at all 4 answers, you can check yourself. Because once you find the right answers, the other 3 ought to be wrong. And toward that, with that in mind, I encourage you to take old exams. In fact, you can take old exams from Physics 1050 because most of the material we've done up to this point is common to those 2 classes. But take them, it serves a bunch of purposes. One is that it shows you what my kind of questions are like. You can learn how to decode my questions and answer my questions. You see what I care about. So if you can identify with each question, what is it that I'm getting at? Why did I ask you this question? Oh, this is a question, for example, that asks you to distinguish acceleration from velocity. You actually see some of the questions you've seen before, because I steal from myself. I reinvent the same questions on purpose or by accident, because there are only finally, there's not that many questions I have to ask, period. I can change the nouns, I can change the verbs, but I pretty much, there was a time when I actually wrote a Mad Lib version of a test system where I could just put in a whole list of nouns. The firefighter did this, the nurse did that, 2 dogs did it. Generate questions. They're all the same concepts coming up over and over. Any questions about the structure? Oh, it's 30 multiple choice questions, 4 answers per. It's on a bubble sheet. So I'll give you a test booklet. Everybody's test booklet will be different. Same questions, different orders for obvious reasons. And bring a pencil. In fact, because I score the bubble sheets, my own computers and stuff, if you can use a pen, it's just hard to change your answer. Okay? Other questions on the exam? My office hours are normally Monday afternoons, the Monday ones. I will pull them forward into the morning, 9 to 11 in Alderman Library, the cafe, the entrance to Alderman Library, 9 to 11 on Monday before the exam, because I know nobody's going to come after the exam. Yes, we're done. Whew, out of here, okay? Any other questions about sort of background stuff on the class? Yeah. You don't need to bring any? No blue books or anything like that. The only thing that you should bring is something to write with. And it doesn't, number 2, number 7, number 1, I don't care. I can read them all. All right? Okay, so where I left off, sort of, I've got a number of effectively physics tools that I need to present properly or carefully, so because we'll use them frequently. And I'm going to go through them. Before I do that, I got at least one really good question that came in. Yeah, do I have extra office hours before the exam? Yes, Monday, 9 to 11. Come and see me. I'll be sitting in Alderman Cafe. Another question that came in it's great. It anticipates somewhere we will end up late in the semester. It says that since same charges repel each other, how are protons held together in atomic nuclei? So you probably, I've said a little bit, and you've probably heard in the past, various contexts, that atomic nuclei differ from one another. The different elements differ in the number of protons they have in the little nugget at the center, the nucleus. It's a tiny piece. It's tiny compared to the cloud of electrons around it. And we will talk about the structure of the nucleus and the structure of the cloud of electrons around the nucleus later on. But just let's look at that little nugget there. With the exception of hydrogen, which has only one proton in it, the other elements, helium on up, they have multiple protons there. And protons are all positively charged. Each one of them carries one fundamental unit of electric charge, positive. And if you bring together these little positively charged things and put them very close to each other, they hate it. They repel each other like crazy. And that's true. So even in helium, which only has two protons, the two protons are not happy to be that close together. And if that's all there were the repulsion between protons, they would just fly apart very happily, and in doing so release a lot of stored energy, because if you grab them with your nuclear tweezers, those two protons, they would push apart, and you could, if you let them go, they would pick up speed, they would accelerate. But if you grab them with the tweezers and let them do work on you, you can get them to move apart at constant velocity, but they will do work on you. You'll get energy out of it. Is that okay so far? What keeps them together is another force, one that will come up late in the semester. We've seen so far two groups of forces, or two forces. Gravity. Any object in the universe attracts any other object in the universe. With gravity, it's related to their masses. It's a relatively weak force. It takes a whomping big object to create noticeable gravity. It is possible in the laboratory to observe the gravitational forces between, for example, two bowling balls, or something equivalent to bowling balls, two cannonballs. It's terribly small, but they do attract each other with forces that can be measured in the laboratory and have been measured in the laboratory. So that's one force, gravity. There's another force, and it's a little fuzzy where the edges are. The forces of electricity and magnetism, they are related forces. So they're basically talked about by physicists as electromagnetic forces. And we've seen that already here in class, that two positively charged balloons push apart. A negatively charged balloon and a positively charged balloon attract. These are real forces. So those are the forces of electricity and magnetism. There are two more forces in nature, fundamental forces in nature, which will show up late in the semester. One of them, they're given creative names. One of them is called the weak force, and one of them is called the strong force. It is what it is. That's what they're called. And the weak force is very weak, and it is relatively inconsequential in most circumstances, including the nucleus for the most part. But the strong force is not inconsequential. It gives rise to a property where if you take two protons and bring them together, at great distance, they hate each other. Don't do this, don't make me go near my brother, my sister, I don't want to. Okay, when they touch, a new kind of force shows up that sticks them together. It's kind of like Velcro, in the sense that it doesn't act at great distance. It's essentially not noticeable at great distance. It isn't until they touch each other, become very close, that it turns on and it's attractive. So it sticks them together. So all the nuclei in us, with the exception of the hydrogen nuclei, which are single protons, they're all held together by that strong force and things related to the strong force. Nonetheless, and so this is where I'm going to go with this is, if you keep packing together protons into nuclei, that repulsion gets stronger and stronger and stronger. It's one thing to bring two protons together. It's another thing to bring 20 of them together. And yet another to bring 100 of them together. Now they really hate it. And this ultimately limits how large nuclei are in our everyday world. The largest nucleus that's just around on our planet has 92 protons in it. It's a familiar nucleus. It's the nucleus of uranium. You want to go much bigger, now they've got to be made synthetically. They're not sort of naturally occurring. Plutonium's up at 94 protons. But the energy that's released when uranium breaks, when uranium nucleus breaks, and this is a big deal in our world, it has been since about the 1940s. If you break a uranium nucleus, its pieces merrily push apart because of electrostatic forces. So if you can get past the adhesion of the strong force and allow the repulsion of positively charged particles to kick in and dominate, lots of energy comes out of this. And this is the nuclear energy of essentially all the nuclear generating plants, the nuclear submarines, the nuclear aircraft carrier, unfortunately, alas, nuclear weapons. It's the breaking of these giant nuclei that have too many protons packed too tightly. It's the release of electrostatic potential energy trapped in those nuclei. And you might wonder, well, where the heck did those nuclei come from? Why did they ever get together? They were produced before the creation of the Earth in exploding stars, in supernovae. During just sort of cosmic catastrophes in which there was so much energy around that a whole passel of positively charged nuclei, positively charged protons could get that close enough to stick together as a team. And they've been sitting around. Uranium is a peculiar, it's a peculiar nucleus in that it spontaneously falls apart because of this terrible repulsion. Eventually, in a statistical manner that we'll come to, what you know of or heard of is radioactive decay. But it has a very long half-life, so it will sit around for billions of years before it finally just goes poof and falls apart. And as a result, we've still got it here, despite the fact that the supernova that created it was at least 4 or 5 billion years in the past. Okay, so long story. It's in our future. Obviously, it's not on the test. But it's something that you might as well know about and recognize this sort of physics. And this physics, the physics of electrostatics, it does show up even in nuclear energy. And you can understand it. Okay? Any questions coming from that? All right. So was there another one? Yeah. My voice is not 100%. It is true. Okay. What I'm going to do is touch on a couple of things that I sort of just assumed and never sort of demonstrated. And then I want to talk more about voltage and issues relating to voltage because they'll be useful to us. So insulators and conductors. We'll actually come back to insulators and conductors and find out why they are what they are in weeks or months. What's the idea here? This is a piece of brass. This is a piece of acrylic plastic. Brass is an electrical conductor, meaning that if I put positive, I don't know, it doesn't actually matter, positive or negative charge on one end, that charge can migrate through the material and along its surface all over the material. It's mobile. Electric charge is mobile in conductors, and it will move in response to electrostatic forces, the forces between charges. So if I put this piece of brass on top of this little guy, remember this is what's called an electroscope. It allows you to see charge by the deflection of that little vein. Yeah, I guess I can do this. The problem with using the cameras is that I forget to undo it, and then it sits there then for the rest of the class. Anybody watching the video gets to watch the electroscope with me talking off in the distance. So this guy will see electric charge if I sprinkle it, if I get it to the scope. But because I put a piece of brass there, so here again I'm getting negative charge. Because I put the piece of brass there, I can put negative charge at the top of the piece of brass, and it will migrate down to the bottom of the piece of brass and onto the electroscope, where the two halves, the rotating vein and the fixed vein, will repel each other. And so this is sort of the equivalent of the hair stand-up trick. I put like charge on the veins, they repel each other, and so the vein sort of does its equivalent of hair stand-up. Is that okay? Why would charge migrate? Well, if I put all the charge on the top of the which I did, on the top of the brass, that charge is packed very tightly. And it hates being all packed up there, so it wants to spread out. It can reduce its total potential energy by spreading out, and it does. So it spreads out off the top of the rod, goes onto the bottom, and goes out onto the vanes. It's happy. It is now settled such that it has the lowest total potential energy it can have without somebody helping it, like to totally escape the electroscope. All right, so now I'll take the charge off, and I do this just cavalierly. I just go and touch it. You know, what am I really doing? I'm allowing the charge to spread out onto me. And I'm big, and I'm also touching all sorts of other things. So it's basically, I let the charge, for all practical purposes, I let the charge escape onto the entire Earth. Okay, if I try the same trick with acrylic plastic, no action. I really am putting charge on that tip of that acrylic there, but it's not doing us any good because the charge can't move. It's on the surface, it's stuck. There's no mobility. And just to anticipate a little bit the physics of why is one material, why can charge move in one material and charge not move in the other? If you just think of atoms, which are at least somewhat familiar, each atom sort of seems to have its own little collection of electrons whizzing around it. And if you touch the two atoms together, well, do they still have their own little collection of atoms moving around? In some cases, yes. So in the acrylic, essentially, yes. They don't share very much their electrons one with the other. That's a little bit of an oversimplification. But basically, you're packing together a whole bunch of little independent beasties that just don't let the electrons go from one to the other. The nuclei, incidentally, the protons sitting in the nuclei, which are also charged guys, essentially never move. In solids, the movement of the nuclei is very unlikely, although there are cases where it happens. It's mostly electrons. You're mostly worried about, can those electrons move around? And in materials, these various plastics and glasses and stuff, basically the electrons get sort of stuck in a little location and can't go anywhere. They got no mobility. In the metals, the conductors, it's different. When you assemble certain elements of the world, copper atoms, silver atoms, iron atoms, the electrons sort of start to become a community thing. Like, oh yeah, each atom has, on average, the right number of electrons, more or less, but there's kind of a sharing mentality in the metals. And so if you put extra electrons in at one end, they get shared around, and then you can find them at the other end pretty soon. So that's what's going on in the brass, is that basically the electrons are mobile because there's a sharing concept going on here. And in the plastics, the sharing's absent. And the details of how that, we'll come to the details of how that works. All right, so the fact that we have electric conductors and electric insulators is helpful just because, and now I want to go back and put this out. It's helpful because, I mean, we just use them. I'm using them all the time up here. So that's the world conductors and insulators. The big Van de Graaff toy here has to have both. It needs the electrical conductor at the top so that we can bring charges there into that conductor, and they then spread out as best they can on the surface. They love to be on the surface. But we also need to keep them up there, so we have to support them on electrical insulators that don't allow them to escape through the material. All right. Why does charge need to have the lowest potential energy? So this is a good question, and it comes back to an issue that I realized I hadn't dealt with last time or the time before, and let me deal with it front and center. And that is, sometimes, I told you from the beginning that objects accelerate in the direction of the net force on them. So if you know what the net force is on any object you like, whether it's a chair or an electron, you know which way it's going to accelerate, or not accelerate if the net force is 0. A term which I will also use and should introduce. An object at equilibrium is by definition an object experiencing zero net force. So this little jar here, can, is at equilibrium. It's experiencing zero net force. So if I use that word, that's what I'm meaning. Okay, so if you know what the net force is on an object, you can tell how it's going to accelerate. But there are often cases where it is super hard to figure out where all the forces are, to sum them up to get the net force. It's too hard. So is there some other way to find the answer? And there is. And it comes about because forces which cause acceleration, forces also show up, yeah, they cause acceleration, but they also carry or underlie potential energies. There is potential energy that is increasing when I take this bottle. Yeah, this water. I would say it's a water bottle, but it's a bottle of pure ethanol, which is, yes, the active ingredient in many beverages. Okay, so if I lift it up and I'm sort of stretching the forces of gravity, I am investing energy in the bottle. And it now has a lot of extra energy. It's a potential energy. It's energy stored in the forces. And if I let go of the bottle, it will accelerate downward. And we can expect that or anticipate it, predict it in two ways. One is that when I let go of the bottle, I'm not going to do it. When I let go of the bottle, it will experience one and only one force, the downward force due to gravity, and it will accelerate in that direction because that's the net force on it. So that's the old way of thinking about it. A new alternative way that's very effective and helpful in contexts where identifying all forces is tough is this bottle will accelerate in the direction that reduces its total potential energy as quickly as possible, which is downward, because it's the only potential energy it's got that we care about, significant, is its gravitational potential energy. And it's got more here than it does there. And the direction it can accelerate that will make its total potential energy decrease as quickly as any direction, we can try them. Left, right, no, doesn't help at all. Go up, oops, counterproductive. Go down, that's the direction that reduces total potential energy. And so objects accelerate in the direction that reduces their total potential energy as quickly as possible. Another example where you can think of that, and it's going to be related to this guy, is suppose you've got a basin full of water and it's higher at one side than the other. The basin, this complicated thing, it might even be sloshing at the moment. This basin has potential energy. It happens to be gravitational again. And if it's got a high spot, it's got more total potential energy than it needs, because it can take the water from the high spot and use it to fill in the low spot. And that will reduce the total gravitational potential energy. So the water will accelerate in the direction, in the many directions that reduce its total potential energy. It'll go to level. It'll go to, how water, the expression is water seeks its level. It tries to go to flat, because that's the lowest potential energy it can have. If it's got any high spot, that high spot can either spread out and get lower, or it can find a low spot and fill it in. All right, so this observation that objects accelerate in the direction that reduces their total potential energy is already useful for predicting what happens to a complicated surface of water. Same thing happens here. If I put extra electric charge on that spot right there on this electrical conductor, and because it's a conductor, charge can move in it. It's like a high spot on the basin of water. It can do better. It can lower its total potential energy by spreading out. So the charges will accelerate and begin to move. They'll develop velocities. They'll begin to move such that each one is desperately trying to lower its personal total potential energy. And they all do that. And when the dust settles and everything's all uniform, they're beautifully spread out on the surface. In fact, they will have the same total potential energy, total electrostatic potential energy per charge everywhere on that surface. That was a careful statement that I'll come back to, because that's voltage. They'll have the same voltage, okay? That's why the charge is spread out. They're trying to get rid of their total potential energy. And if you really want to go into the details and you look at the forces on every individual charge, you will find that it's in the same way. And yes, you went to great effort to do that, and it wasn't worth it because there's an easy, speedy solution. Look for the total potential energy. Okay? Okay. If that were not a conductor, it wouldn't happen. The charges would try to produce their total potential energy, just as this bottle would love to reduce its total gravitational potential energy, but it can't get there. It can't. I have to help it get mobile, and now it can do it. So there are situations where you've got trapped total potential energy that you can't break free of. All right. Voltage. So now I wanted to go to voltage. I started doing this on Monday, and I wasn't good. So what voltage is, and it's something that you have encountered many times in the past, whether you know it, whether you understood it or not. Voltage is a characteristic of a location. It is, so every place in space, in fact, places where there's nothing, have voltage. There's the voltage of that spot right there. And what voltage is the amount of work that one unit of electric charge at that location would do on you if you let it move away from that location off into basically deep space, somewhere where there was no electric charge effects left. So the way you conceptually make this measurement is, I want to know what the voltage of that location is. How do I do that? I'll put some charge there, and you usually, conceptually, you go in there with what's called a test charge, because the test charge is like ordinary charge, except it doesn't influence anything around it. It just feels the influence of what's around it. If you went in with real charge here, it would push stuff around. It would polarize me, and it would stick to me and stuff. I don't want that. Just put in a thought charge, conceptual charge. We put it there, and now let's see what kind of work it will do on me as we go off into deep space. And suppose it pushes my hand as it's leaving this spot. It's pushing my hand, whoa, and I have to hold it back. It's dragging me. It's doing work on me as it's doing this. Whew, off we go, and now it's in deep space. It did 100 joules of work on me. And let's imagine that this is 1 unit of charge, which is, again, the unit of charge is the coulomb. So 1 coulomb at that place did a whole 100 joules of work on me. This is a location then where positive charge has excess energy. It's electrostatic potential energy associated with the electricity. And it's got 100 joules per coulomb of excess energy. Every coulomb, if I came over there with a second coulomb, would do another 100 joules of work on me. So it goes per coulomb of charge you're worrying about. That means this location in space is 100 volts. That's what 100 volts means. 100 joules per coulomb. Every coulomb that lives at this location is able to do 100 joules of work as it leaves that location for far away. Now, why would it have that energy? Well, because maybe this location in space actually had a whole lot of positive charge in it or around it. It's now a place that positive charge hates. So if I illustrate this as packed full of positive charge, it shouldn't be so surprising that my little test charges want to leave. Get me away from that thing. It's light charge. Hate it. So this is positive 100 volts. If we pack more and more and more positive charge here, then it gets, our little test charges are more desperate to leave. They'll do more work on us to go away. So the voltage goes up. So the voltage at a location typically increases as the amount of positive charge near that location increases. All right? The positive charge doesn't have to actually be at that location. It could be a whole structure around a horseshoe around it. A positive charge would hate to go into a horseshoe the gap in a horseshoe if that horseshoe is covered with positive charge. Bad news, okay? The other possibility that would happen is, suppose, erase that whole story. We go here again with a test charge. We want to see what's it like, how much work will the test charge do on me as it leaves this place? And suddenly I discover it likes being there, and I have to drag it away. I'm pulling. I'm doing work on it now. It wanted to stay. Don't make me go. I'll be good, I'll do my homework. This location in space now is a place that positive charge does not want to leave, wants to go to. So positive charge at this location has, you need energy to drag it off into far, far away. This is a location of negative voltage, less than 0 voltage. The energy per charge, where charge, if I don't say it's negative charge, charge is a positive amount. It's like, again, it's like my quip about giving money to charity. If you give money to charity, we assume it's positive. If I talk about charge, we assume it's positive unless I say otherwise. So if you discover that positive charge wants to stay here and you have to drag it away, this is a location where the electrostatic potential energy per charge is less than 0. You have to pay. It's basically got a debt of electrostatic potential energy. You have to pay to pull the positive charge, the charge, away from this location. All right? So the world has the whole variety pack of positive voltages, which charge will do work on you as it leaves, all the way down to negative voltages, which charge will do negative work on you as it leaves. All right? And the world of sort of electricity as we use it normally, which is electricity carrying electric power and doing things, whatever, it's all about receiving electric charge, positive, at high voltage, sucking the energy out of it and returning it to somebody at low voltage. That's what we're doing. All the power lines, all the batteries, that's what they're doing. Generators. They're giving us electric charge at high voltage, chock full of electrostatic potential energy, able to do work. We take that energy, do something interesting with it, make light, make motion, whatever, make heat. And then now we've got the charges at low voltage, having lost all that stored energy, that electrostatic potential energy recharge. And we send them back. And why do we send them back? Because charge, if you accept charge, say, from the power company, so I'm anticipating the story of flashlights. If you take electric charge from the power company at high voltage, yes, it comes chock full of energy. This is all good so far. You now use that energy, and now you've got charge at low voltage, and you just put it in your sock drawer. And you do that again. You put the charge in the sock drawer again, and you put the charge in the sock. Your sock drawer is going to have some problems pretty soon. It's now got more and more positive charge. It's not going to want any more positive charge. The flow is going to stop. You can't take any more charge from the power company because now you've got high energy charge where it's all packed together. So what are you going to do? You don't want to accumulate charge. Send it back. Let them put more energy in it. Take it again. So this is the origin of electric circuits. You've heard of circuits. The reason we operate electric circuits as a way of delivering electric power is because our goal is to receive energy from the power company, not to receive charge. You can't do anything with it. You just accumulate it for a while, and then you have lightning bolts fly out of your fingers. Send it back to get more. We could have, instead of an electrical system doing this, we could actually have a water system doing it. We could have the water company send us high pressure water, which is also chock full of energy per liter, per drop. You could use that energy to do things. We operate certain devices in our house on water pressure alone. For example, a toilet. What's operating the toilet? It's water pressure. So the water comes in, you take the energy out of it, But we don't really want to have a water-powered system because eventually you're going to have an awful lot of water in your house. The water comes in, you take the energy out of it, and then you just put the water on the floor. And take the water in again, take the energy out, and put it on the floor again. Pretty soon you're going to be up to your eyeballs in water. So send it back to get more energy. All right? I'll stop my analogies. I usually get lost in them. All right, so this device here, which is, yeah, maybe. Yeah.
Then wouldn't that get more electrostatic potential energy because you're packing them together, and wouldn't it just be high voltage?
Exactly. Yeah, so Maddie, right?
So why do you send it back?
It's because if electric charge comes in, so her question is if electric charge comes in at high voltage, you take the energy out of it and put it in your sock drawer. If you keep doing this, doesn't your sock drawer become higher and higher voltage? And the answer is yes, which means you can take less and less of the energy out of the incoming charge and still get it in your sock drawer. Because if you bring it in at 1,000 volts and then you suck all the energy out so it's at 0 volts, you can't get it into your sock drawer after there are a couple charges in there already. It's going to be repelled. You have to push. So you can't go to 0 volts anymore. You only go to 1 volt because you need enough energy left for it to go into the sock drawer. And in a couple hours, it's going to be up to, your sock drawer is going to be at 500 volts. You're going to only get half the energy. And pretty soon, you're going to be the energy source. You're going to get no energy out of the charge at all. It's going to come in, you're going to have, your sock drawer is now going to be the highest energy thing around. So that's why you can't accumulate. There are certain situations where you're going to accumulate it briefly, but they run into trouble. This, for example, is basically doing that. It's doing the sock drawer. It's trying to accumulate more and more and more, what? There happen to be negative charges, awkward, but it's true. Once they're in there, you can't get any more on it. They're repelled. So this actually bogs down eventually. The motor begins to struggle because it truly is trying to deliver more like charge to a thing already full of like charge. And eventually it can't actually deliver anymore. They're leaving as fast as they're arriving. If they didn't leave the top for reasons having to do with sort of leakage, the motor would eventually stop. It couldn't actually move the charge up there anymore. It couldn't push hard enough. Other questions? Again, questions are good. I mean, otherwise I leave things out, and also there are surely questions other people have. So this accumulates negative charge more and more, and as it does that, the strange thing that happens to the top, its voltage goes negative. It becomes a place that positive charge does not want to leave, that you have to drag positive charge off of. Positive charge wants to go there. So it goes to about negative 100 or 200,000 volts. It's a huge voltage. It happens to be negative because it's a place that positive charge loves to go to. And the test charges that scientists and engineers think about are always positive. All right. Actually, the hair stand-up trick is also the hair. You put the charge all over your hair, and we now have a mirror so that those of you who want to try this after class, you can see yourselves. The charges can reduce their total potential energy by spreading out still more, and they do it now on hair. Charge is not very mobile in hair. It's more like plastic than it is like brass. But the hair can move. The hair itself can move, so the charge actually drags the hair with it to give these dandelion-shaped hair look styles. All right? So that's the story of voltage. And I think I've done that one okay. Now, next thing to go on, and where am I heading? I'm heading towards electrostatic copiers, zero-graphic copiers and laser printers. A little bit of history. Xerox Corporation, which you sort of still hear about, was a big deal when I was a lot younger. Having invented a way of essentially doing photography with electrostatic charges, with charge. They could take an image of a sheet of paper, a document. They could essentially photograph that document, create a pattern of electric charge that had a one-to-one relationship with that document, stick colored powder on on that electric charge and transfer it to a sheet of paper. So that the xerographic printing or copying concept was all about controlling the placement of electric charge and therefore controlling the placement of little tiny pieces of powder, what you call toner. You know what's toner? It's little tiny bitties, little plastic powder, probably in a liquid. So it's got some mobility. And the idea is pretty simple, finally. You take a surface that does not conduct electricity, so that if you put charge on it, the charge sits there. You decorate the whole surface with electric charge, which is not a trivial thing to do. So you put like charge, positive, or in some cases all negative on that surface. And on the surface is actually thin, and it has metal on the back. So the charge is sitting on essentially a plastic surface, a non-conducting surface, with metal on the other side. That metal is connected to the earth, effectively. So that if you put negative charge all over that surface, that negative charge attracts positive charge onto the metal on the opposite side. The two surfaces are staring at each other. Here's the charge you put on the exposed surface. Opposite charge runs up and sits just across from it, attracted there. And it shows up until the two are essentially electrically neutral grand total. They have a net charge of 0. But they're staring at each other across a gap that's non-conducting. And that's the situation until light comes along. This electrically insulating material is special. It's called a photoconductor. It's a material that becomes electrically conducting when exposed to light, and we'll see how that happens down the road. So it goes from being electrically insulating and keeping the charges apart to being electrically conducting and letting them get together, and they cancel each other and they're gone. And they do it very location specific. So you can erase the stored charge on tiny little spots of the surface by hitting them with tiny little spots of light from either a document through a lens or the laser. And so that's the concept behind the laser printer or xerographic copier, is put the charge on the surface, have the opposite charge show up through the metal to join it. Basically, it's polarizing the metal in the world. And then erase the parts you don't want to have charge on using light. At that point, it's just a matter of bringing up powder. You bring up the black powder, it sticks to the charge because it polarizes. Remember, charge loves to stick to stuff, and stuff likes to stick to charge. So you pick up all the powder, you then transfer the powder to the paper. There's a little bit of trickery to get rid of the charge so that the powder transfers properly to the paper, and then you fuse it into the paper with heat and pressure. And that's all you're printing. So you've done this, all of you have done this many times. So what's left, apart from that story, what's left? Where's the physics? Well, there's some physics in turning that photoconductor from electrically insulating to electrically conducting. That's a trick. That's a pretty sophisticated little trick. How do you make a material like that? We'll get to that. It's not for today. What is for today is how do you sprinkle charge down on a surface? How do you put a nice uniform coating, paint that surface with electric charge? And the answer to that is that you use a high voltage piece of metal, you put charge on it, and you get the charge to jump off the metal onto passing air molecules. And from there to ferry, the air molecules then ferry them onto the surface. So you want to get the charged particles to leave the metal, go onto the air molecules, and from there onto the surface. How do you get them to leave the metal? Well, one way to get them to leave the metal is to put such high voltage on the metal that the forces between the charges are so ferocious that they push charges right off, and the charges just leap off in these uncontrolled sparks. Just once they go, it's just a catastrophe. Once a few of them get going, the whole team goes. Well, that's not a very good way to put a nice uniform layer of charge down on the surface. You want a very controlled situation where the charge is just going off gracefully onto the passing air molecules and then gets ferried nicely over to the surface. Once they get on the air molecules will love to go over to the surfaces because they polarize the surface, they draw opposite charge nearby a little bit, and then they are attracted and they go and they stick and they're happy, and they like to make uniform because if they all pile up in one location, they repel each other and they want to spread out. So physics is helping you, but the issue is trying to get the charges off the surface in the first place, onto the passing air molecules. And the way you do that in a graceful manner is what's called a corona discharge. And so I want to give you an idea of how a corona discharge works, and it requires developing some physics that I'm not going to get to today, but do I want, no, I don't want to do it that way. I do have a question here. Where is it? Yeah. Let me ask, late in the day, but sorry, it is what it is. Here it is. Here's a question. You're covered with static electricity. If you hold a sharp pin in your hand as you reach out for the doorknob, so without the pin, you walk over the doorknob, a little lightning bolt shoots out of your finger. But no, so you've done that a million times, right? You've gotten a shock from touching some piece of metal when you're covered with a charge. What if you reach out with a pin instead of your finger? How does that affect the spark? You okay with the question? For those of you who are willing to pull out your clicker, click away. There we go. Five, 4, 3, 2, 1. It's a bit of a spread, but B is the winning vote here, and the shock is weaker. So let's try it. I could cover myself with charge and go and reach out to the ball, but I'm going to do the reverse. I'm going to cover the ball with charge and reach out to the ball with a needle. It turns out it doesn't matter whether I have the charge or whether it has the charge. It's going to draw charge onto me. When it's negative, I'm going to be covered with positive charge anyway. It's going to pull it up onto me. Watch what happens to the spark. So here's the spark with my knuckle. I can get hit from out here. It's getting me. If I go up there with a needle, nothing. I ruined it. What happened? Well, here's what happened. So, that was a good one. All right, it is possible to get. Here's what happened. That ball, being negatively charged, pulled positive charge onto me and onto that needle. The positive charges piled up on that tip. Lots and lots of them there. And they are so tightly packed, they push especially hard on each other right there. So it has a very strong equivalent well, it's what's called a voltage gradient, also known as an electric field. And this is I'll do this on Friday. There's a lot of electric field right near that tip, meaning that every positive charge in that location is being pushed ferociously, so ferociously that it wants to move, and they will leave the tip onto a passing air molecule and then ferry over onto the ball. So instead of shooting these uncontrolled lightning bolts at the ball or at me, I was spraying it gently with positive charge. So it was getting negative charge on it because of the belt, and I was just sprinkling like a salt shaker positive charges out of that tip. And in a dark room, really dark room, you usually can see it. It's a glow. It's called a corona discharge. It's a purple glow of the air receiving the electrons jumping out of the tip, glowing as a result, and then ferrying over onto the ball. So the ball can't accumulate very much negative charge before I just discharge it with positive charge. And corona discharges show up not only in this context, but some of you have come up and done the hair stand-up thing, and you're welcome to do this after class again. And you feel these sizzly sensations and something coming out of your fingers or any sharp object you got. Those are corona discharges. They are all over the place. They're around electric power lines. They're part. St. Elmo's fire. What's St. Elmo's fire? It's corona discharges around the masts of ships when they're covered with static electricity. So, okay, with that, then we'll stop, and I'll finish xerographic copiers and laser printers on Friday, along with starting flashlights.